So this whole concept of formal charge is going to be kind of looked at right here. So sulfate. So right, sulfate is S, okay, SO42 minus. So obviously sulfur's in the middle with 1, 2, 3, 4 oxygens. And then sulfur has 6 valence electrons. So 1, 2, 3, 4, 5, 6. It's a little bit bigger than I wanted. And then the oxygens also have 6. So 1, 2, 3, 4, 5, 6.
You're not sharing your
Oh,
screen.
shoot. Thank you. At least you guys speak up sooner. Some of my classes don't tell me till I've like gone through a couple slides. Because I'm not, constantly looking at the chat. Thank you. Oh, I don't like that. Okay. Now, you have to bond everything at least one time. Otherwise, there is no point of drawing these. You must create at least one bond. Oopsies. I put that 6th electron in the wrong spot. So again, we're splitting up lone pairs because like we have to. Okay. Let me know. You can go ahead and put in the chat, how many of you have double bonds in your structure? You could just write me. So 3 people at least have double bonds. I haven't included my 2 extra electrons. I will in just a second. So let me do that right now. So these 2 extra electrons allow me to add electrons. So I'm going to add it to arbitrarily to whichever oxygen I feel like. So I feel like left, right. Okay, great. So it looks like a bunch of you have some double bonds present in your structure. Is there anybody who has all single bonds? Anyone? Okay, so let's talk. Looks like a handful of you have double bonds, so I'm guessing you took this lone electron and this lone electron and paired them up. Ooh, yuck. Which is fine. And then because I put my electron here, you probably took this lone electron and this lone electron and paired them up. So now you have this. I talked about the lines, right? Did I talk about the lines for lone pairs instead of the dots? Please say yes. I think I might have skipped it in my second period on accident. Okay. So, and then you put the brackets. And this is a possible Lewis structure for the sulfate ion. Now, before we move on, how many different ways can you draw this? Meaning, how many resonance structures are there? Which means, how many different ways can you manipulate these double bonds? So this is one way, right? This is one resonance structure. So I'll give you a second to count. Now this one has a lot more, right? So top and bottom would be one, right? What about left and right with the double bonds? So that'd be a second one. Left and right, right? What about top right? So here and here. What about here and here? What about here and here? Here and here. Oh, there are 6 different ways you can draw this, meaning there are 6 different resonance structures for this. Okay? questions so far? What's the bond order? So let's refresh our memory on how you do that. For bond order, you count how many bonds there are. There are 1, 2, 3, 4, 5, 6 bonds. And then you divide it by what are called the bonding domains, aka how many things are bonded to your central atom. 1, 2, 3, 4. So 1.5. So these bonds, so this guy has a bond order of 1.5, 1.5, 1.5, 1.5. It isn't like 2, 2, 1, 1. Really, these electrons right here and right here are evenly shared without the ion. That is what it means to have resonance. Okay? They're evenly shared throughout the entire ion. This bond is the same length as this bond and this bond and this bond. They are all the same length. So while we draw it with 2 double bonds and 2 single bonds, it's truly somewhere in between a double and a single bond. Okay, now, someone tell me how I could draw this with all single bonds. Oops. Let me put in my extra electrons and then Winston's gonna go for it. So here's my extra electrons. I put them in red, my 2 minus. So Winston, go for it.
Did you transfer sulfur's electrons to make the oxygen stable?
I did. Because remember, yes, while they come from sulfur, they don't truly belong to sulfur. They belong to anything else or anything in the structure that needs to have its octet achieved. So I can do this. So that first way we did it, sulfur had an expanded octet, which there's nothing wrong with that. Sulfur is allowed to have an expanded octet. So this way, sulfur does not have an expanded octet. It has exactly an octet. I gave one of the electrons to the oxygen to complete its octet, and I gave the other electron to the other oxygen to complete its octet. This is an alternate Lewis structure. This is a possible Lewis structure. And then again, sorry, you need the brackets and the 2 minus. So then what happens is you go, well, which one is better? Like in life, which one are they seeing more of? Now, okay, here they are. Let's look at formal charge again. So we ended with that, so we're going to kind of redo this so we can refresh our memory on formal charge. Let me move this. So remember, for formal charge, what you do, the first thing you do is you look on the periodic table and write down how many valence electrons every element should have. So sulfur, according to the periodic table, has 6. Oops. 6. All the oxygens also have 6 according to the periodic table. 6, 6, 6, 6, 6. Okay? Then what you do is you subtract how many have actually been assigned to them in the Lewis structure. So like this oxygen has been assigned 1, 2, 3, 4, 5, 6. Oop, I lied, sorry. Oop, 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 oop. Okay, sorry, 1, 2, 3, 4, 5, 6, and then you only count one of the ones in the bonded pair, 7. So 6 minus 7. So this oxygen's formal charge is -1. 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1. 1, 2, 3, 4, 5, 6, 7. -1. Sulfur, 1, 2, 3, 4. 6 minus 4, +2. Ooh. So this one has formal charge everywhere. Every single element in this ion has formal charge. Okay, now remember the formal charge should add up to the overall charge. So -1, -2, -3, -4. Wait, -1, -2, -3, -4. Am I missing something? Oh, sorry. What's this? 6 minus 7. I keep counting it. This is not, never mind. So 1, 2, 3, 4. So -4 plus 2 is -2. Okay, so it should still all add up to -2. If we're not doing this for an ion and it's just like a neutral molecule, it should all add up to 0 because it doesn't have charge. So let's look at the formal charge here. Well, oxygen has 6 valence electrons, and I've given it 1, 2, 3, 4, 5, 6. No formal charge on that oxygen. 1, 2, 3, 4, 5, 6, 7. So -1 on this oxygen. 1, 2, 3, 4, 5, 6. So 6 minus, 6, that's this one. 6 minus 6 is no formal charge on this oxygen. 1, 2, 3, 4, 5, 6, 7. 6 minus 7, -1 formal charge. Sulfur, 1, 2, 3, 4, 5, 6. 6 minus 6 is 0 formal charge. So the structure on the right has less formal charge than the structure on the left. Now, I taught you that lower formal charge, it tends to be a more stable or a more common ion. Okay? The thing is some scientists will argue that having an octet and not an expanded octet is more stable than low formal charge. And to this day, people don't agree on it. Some scientists will say not like having this octet around sulfur as opposed to an expanded octet is better. And some scientists say, nope, expanded octets are better if the formal charge is lower. So which one's right? Don't know. Can't even tell you. Both of them are right, and it depends on who you ask which one is better. So what you're subtracting is how many electrons have been given to it in the structure. So the first number we start off with is, according to the periodic table, sulfur has 6 valence electrons. So I wrote 6. And then what you have to do is you have to count. So I'll erase all this. You have to count how many electrons. So it has 6, according to the periodic table. And we're going to subtract how many you've actually given to it. 1, you only count 1 from the bond. 2, 3, 4. Okay, so like for this oxygen right here, oxygen has 6 according to the periodic table, minus we've given it 1, 2, 3, 4, 5, 6, and then you only count 1 from the bond, 7. And so that's a formal charge of -1 on this oxygen. So we didn't have this issue with the thiocyanate. We picked this one, and it was this one for certain. Hello. Sorry, guys. So we picked this one, and it was this one for certain because it had the lowest formal charge. This guy had the highest. So then we had to choose between these two because they actually had identical formal charges, 0, 0, -1, 0, 0, -1. And we picked this one because the formal charge, the negative formal charge, was given to the more electronegative element. And we didn't have this fight about expanded octets or complete octets because every single thing in here only had an octet. Okay. I'm going to go back now in the notes to a couple of things that we skipped. The first thing is was this one. So it says the bonds in the NO bonds in the nitrite ion are equal in length and they are unequal in HNO2. Oop, this should have gone after. I lied. Wait, what's happening? Sorry. Okay. See, this is what I'm talking about. My screen recorder is such a pain sometimes. We'll do this second. Oxy acids. So this is H2SO3. And this is just, I don't need you to draw it. Just know that oxy acids, so these are acids with oxygens in them, like a polyatomic ion that has oxygens. The hydrogens, the acidic hydrogens, right, this is what makes it acidic, are always attached to the oxygens. So I need you to just know that. This looks like it's missing some dots. Okay, the acidic hydrogens are always attached to the oxygens. So you just need to know that, which will help us now answer these other two questions. Okay, so the NO bonds in the nitrite ion are equal in length, whereas they are unequal in HNO2. So here's what I would do. Please draw nitrite and please draw HNO2. So this is what I was just saying. So this is an oxy acid, meaning the hydrogen is not attached to the nitrogen. The hydrogen is going to be attached to one of the oxygens. Which one? I don't care. It doesn't matter. So go ahead and try to draw nitrite, and then go ahead and try to draw nitrous acid. Oh gosh, I wrote. See, my notes are out of order. Okay, do not draw this with two double bonds. I'm going to right now, and you're going to tell me why not. Oh, well, you can't, but nitrogen cannot have an expanded octet, so please don't let it have one. So double bond. I could have just as easily put the double bond this way. Now, I do get one extra electron, which works out really nicely in my favor, right? Because this one just needed one more. Okay, so did you draw HNO2? So remember that the hydrogen goes on either of the oxygens. I don't care who you pick. Fine, pick this guy. If you give the electron to N instead of O, you don't then have an octet on oxygen. Okay, so again, let's go back to the question. It says the NO bond lengths in NO2 ion are equal and not in HNO2. So why? This guy has resonance. And if you want to explain it, I would say 1, 2, 3 bonds divided by 2. It has a bond order of 1.5, meaning this bond length and this bond length is somewhere in between the length of a double and a single bond, both of them. Ooh, does this guy have resonance? This is a double bond. This is a single bond, which was great when it was just oxygens attached to the central atom. Now it's not. There's a hydrogen attached to here. So you can't just flip this double bond. If you flip this double bond, you move the hydrogen over here, which is the same exact compound. So this guy has a double bond and a single bond. Double bonds are shorter than single bonds. This has a bond order of 2. This has a bond order of 1. Double bonds 2, single bonds 1. And it doesn't have resonance. So this is shorter and this is longer. Remember with resonance that these 2 electrons right here are shared evenly throughout the entire ion. Questions on how to answer that problem? Okay. So here you go. I want you to do this on your own. Meaning I'm going to pause myself and I'm not going to screen share. And I want you to write down what you think is the best answer possible to get full credit on a FRQ from 1999. I was in high school in 1999. Okay, go. Now we're going back. Okay. I'm going to be honest with you. I don't need you to know this in depth, but I am going to do my best to explain it to you. Again, I don't need you to know this in depth, but this has to do with the sigma and the pi bonds and
I don't think you're sharing your screen.
Electrons. Okay. So these electrons with resonance are called delocalized electrons. What that means is they have the ability to be kind of shared evenly throughout the molecule by multiple atoms. So if you see this guy's name is benzene, and they often draw benzene like this with a circle around it, meaning instead of assigning the electrons to specific carbon-carbon atoms, right, that could be done a different way. They say, okay, all these electrons are being shared throughout the entire molecule evenly. So they're called delocalized electrons. Delocalized just means they have the ability to kind of move around freely within the molecule between different atoms. Now, how this happens is kind of complicated. Again, I'm going to repeat, I do not need you to know the in-depth part of this, and you don't need to know it for the AP test, but this is going to be where the sigma and the pi bonds come from, like how they got their name, and it has to do with the overlapping of orbitals. So if you look at, let's see. So if you look at, this is the benzene ring. You got carbon, 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 carbon. It's 6 carbons in a ring, okay? And then there's also double bonds involved, and they're alternating. So like double bond here, double bond here, double bond here. Or I could have put it here, 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 right? That's the whole point of resonance. But let's just look at it this way. So what that means in a double bond, remember in a double bond, I told you before, you have a sigma bond and a pi bond. And a sigma bond is the overlapping of s orbitals, okay? And it's a direct overlap. So here's an s orbital, right? They're spherical. Here's an s orbital. There's 2 electrons. That's not a very good drawing. I'll draw it here. So here's an s orbital on one carbon atom. Here's another s orbital on another carbon atom, and you've got the 2 electrons, right? So here's carbon, Like this carbon has 1 electron. Say, okay, they're being shared in a direct overlap. This is called a single bond. So a sigma bond involves these 2 electrons right here. So we draw them like here and here, right? The electrons, but really it's an overlapping of the electrons that create this bond. Now, in a double bond, you have 2 more electrons. So what happens is, right, there's only a single s orbital, right? But the p orbitals have 3 different kinds of orbitals. P or PY, PX, and then PZ. Okay, so if you look back here, okay, these would be, so they called these I think they showed those as PX, but really I'm going to call them PY since they stand up and down. So these are the p orbitals that carbon has, right? Carbon is 1s2, 2s2, 2p2, right? That's carbon. So you have p orbitals present in carbon, all right? And you have electrons in them. So what happens is these electrons are considered delocalized, meaning, let me see if I can draw in here. So like there's an electron here and an electron here, let's say, in some of this region, okay? And so like they share in the double bond, right? And then like an electron here, and they share in the double bond. An electron here, and they share in the double bond. Well, really though, they don't belong here and here. They could just as easily be, I'm drawing a different color, here and here, and here and here, and here and here. So what does that mean? It means these electrons actually freely kind of move around in these overlapping p orbitals, okay, around the atoms that are not a direct overlap like the s orbitals, okay? And so you can see these like delocalized electrons really just kind of moving freely around, and this is what it means to be called a pi bond. A pi bond because of the p orbitals, okay? And that's kind of how we get this resonance concept. Ooh. Okay, again, I don't need you to know this in super detail, but that's where the pi bond concept comes from, is these overlapping of the p orbitals instead of a direct overlap from s orbitals. So let's say we did like, I'm going to do a simple one. So hydrogen is 1s1, right? So it has an s orbital that has one electron in it. Chlorine is 1s2, 2s2, 2p5. But there's only a single bond right here. So what's going to happen? I'm going to draw chlorine in different colors so you can kind of see. Chlorine. 1, 2, 3, 4, 5, 6, 7. Okay? The overlapping of chlorine's s orbital and hydrogen's s orbital is what makes this bond. Okay? There isn't a multiple bond, so it's not that chlorine doesn't have p orbitals, it just doesn't have p orbitals that are involved in a chemical bond, okay? It's where my lone pairs of electrons are being stored, okay? So this is a sigma single bond. It's when you get to multiple bonds that you start seeing the overlap of p orbitals, which are what are known as pi bonds. So carbon, I'm going to do C2H4. Ooh. Whoa, I drew that a little bit far away. Okay, the carbon-hydrogen bond is a single bond. Is that right? So, right, carbon. I'll line them up so that they look nice, right? 1, 2, and then these are going to go here, right? Well, I'll do it like this. I should have given them different colors. Okay, I'll talk about the P in a second. So this is hydrogen. Hydrogen, hydrogen, hydrogen. So this is an s orbital, and this is an s orbital, direct overlap. S orbital, direct overlap. That's what creates this bond. S orbital, s orbital. I should have been sharing, but direct overlap. S orbital, direct overlap, right? These guys are sharing in a single bond. They call them sigma bonds. They are the s orbital and s orbitals overlapping, direct overlap, okay? And then now it also shares here, right? So this is a direct overlap of the s orbitals, okay, being shared. Now, carbon's not full yet, right? So the s orbitals for carbon have already been used. There's only an s orbital, right? After s orbitals come p orbitals. So what happens is each carbon has a p orbital, right? 1s2, 2s2, 2p, 2p2, sorry. Okay? So like this carbon has an electron, and this carbon has an electron. This is for each carbon, right? And they're either up here or down here. It doesn't matter. But in order to create the multiple bonds, so these guys are like sharing, meaning the electrons are like can move anywhere in these. This is a p orbital. I'm going to call it py. And each carbon has one. So this overlap right here of these two electrons is what creates the double bond. It's from these p orbitals. Okay? So again, they call them this is called pi bonding. So that happens when you have a double bond or a triple bond, okay? Pi for the p bonding. So these two electrons can go anywhere around here to create that double bond. They're delocalized. Okay? So I'm not going to go into any more detail on this. It probably went into way more than you ever needed to know for this class. If you ever take college chemistry, you'll go into a lot of it. But that's what it has to do with p orbitals and pi bonding, okay? Okay. Sorry, I want you to do this before. Please draw NO2, not NO2 minus, NO2. It's gonna make you sad. Well, it makes me sad. Maybe it won't make you sad. Please draw NO2, nitrogen dioxide, that nasty toxic brown gas. I don't know if you've noticed, but we haven't worked with anything that has an odd number of electrons yet, but we're about to. Uh-oh. I don't have any extra electrons. So like when I did nitrite, I got to throw in an extra electron, which I gave to this, which made me be able to have an octet. So I don't have that. I cannot form a double bond because you will then have an expanded octet around nitrogen, and nitrogen is not allowed to have an expanded octet. So what do I do? Wow, my Zoom is like not letting me do anything. So I can't read the chat. Does anybody have anything they could say out loud? Okay, well, like I said, I can't do anything right now on my Zoom. I can't even go back to, oh wait, where is that? There we go. Oh, I have access to the chat again. Okay. This is going to go along with the concept of formal charge. What does that mean? Who gets to be stable first if you have to choose? And we do have to choose in here. Who gets to achieve stability first? AKA, who's going to get the electrons? the more electronegative one. Why? Well, because it's going to yank on the electrons harder, so it'll attract electrons more, so it will achieve stability before any other element that's less electronegative than it. So having told you that, what do I need to do? Yeah, oh no.
Yeah, they'll extend.
Sorry, nitrogen.
Coverage over to all named operators. No, I mean it's be no different if somebody was 70 that was on a policy. Yeah, there's no age
Oh.
limit.
You have to lose your electron. So now I have 8 here, 8 here, and 2, 4, 6. Oh, so sad.
As far as coverage, there's no limit.
It's just the way it is. This is its structure. It has an odd number of electrons. And you go, well, how is it stable? Well, this molecule and these all of these atoms, nitrogen and oxygen, are both really, really small atoms. And so it is okay being like this.
Yeah.
I don't see these very often on the AP test anymore, but this is the Lewis structure for NO2. Yeah, nitrogen got robbed. You lose an electron, you just got to move on. I think that it gets back at everybody by being a poisonous gas. That's like my assumption. It's like, oh yeah, you're going to not let me finish my octet? I'm going to be poisonous to you. Pretty rude, but you know. All right. So, NO2, odd numbers. Obviously, the more electronegative element will achieve its octet first because it will attract the electrons around the molecule better. Okay, last thing. I'm pretty sure this is the last thing. Overlapping and bonding. So there is like a perfect ideal distance that two atoms can be away from one another. And again, it depends on the two atoms involved in bonding. So I need you to be able to read this graph. Okay. So what this is saying, so this is just hydrogen, hydrogen. So this is just H2. We're looking at H2. So what this is saying is that H2 distance. So this is close together. And this is far apart, okay? Right at the bottom, the wherever the biggest dip is the most ideal distance. Meaning, in other words, if you read this, this is the energy that's released or absorbed when the bond is formed. So this is the maximum energy released when the bond is formed. So this is the most ideal distance. Which means if you put two hydrogen atoms too close to each other, the nuclei get too close to each other. What do protons do to other protons in each nucleus? Well, they repel. So they don't want to be next to each other. So what this is saying is this is like way too close. They're too close together. This is the best. So then you spread them out, spread them out, spread them out. This is the best you can get. If you keep spreading them out, eventually they'll be too far apart, right? And if they become too far apart, they can't even recognize each other, so they can't bond. So there is an ideal distance for every single substance and every single chemical bond that two elements want to be from each other. And that distance is wherever the most energy is released. Okay, so again, when you read this, this is ideal as it gets. This is the best distance. This is too close. This is too far. Look, they're so far apart here, they can't even bond. They're like not even bonded because they're not even close enough to each other to recognize each other. Here, they're way too close together, which means the two nuclei are going to repel each other. Okay? So again, that's all you need to know for this. And look, this is how much energy is released when hydrogen bonds to itself. Remember, bond formation is exothermic. Everything I just said is right here. Okay? So something we have not talked about yet is the bond type when it's the same. So if you remember, we said bond dissociation energy goes in this order. Bond dissociation energy is the energy required to break a bond. So single bonds have the lowest, I'm going to write it bond dissociation energy.
I don't know, that's what
That looks like an O.
I think if I die, they could get it.
Okay. And then triple bonds have the highest. They're the hardest to break. So now what we're going to do is we're going to look at it. We're going to compare things that only have single bonds. Because, right, we said hard, easy to break, hard to break. What if they all have single bonds? How do you compare their just bond association energies? Well, let's look. So they have carbon chlorine, carbon bromine, and carbon iodine. Just a carbon chlorine bond. So carbon, chlorine, carbon, bromine, carbon, iodine, right?
Yeah, this is the one with the code. Yeah, I need to find
Okay. So on the right atomic trends, chlorine is the smallest halogen out of these three, and iodine is the largest halogen out of these three. So what does that mean? Well, carbon's the same for all of them, right? They're all attached to carbon. So it's not the carbon that's the determining factor, but they are all single bonds, but one of them is stronger than the other. Who's the strongest single bond and why?
Yeah, if you could find one. If not, we'll just.
So this one has the highest bond associated energy, and this one has the lowest. What does this mean?
I know there's one like prison, but that's pretty far.
Hard to break, easy to break. Why? Why is this guy the hardest to break and this guy the easiest to break? So chlorine is small, boy. What does that mean? So what? So chlorine is smaller, which means the carbon and chlorine atom can get closer together. What do you know about the electrons involved in a bond that can get closer to the positively charged nucleus? They are more attracted. If they're more attracted to the nucleus, they don't want to get ripped apart. Look at the carbon and iodine. Iodine is a much larger atom, which means the electrons in here can't get as close to the nucleus. This bond length is much longer, which means a longer bond length, further apart, easier to break through. Right? Think about like, I know I keep using karate chopping. Let's say you have two bricks. Those are our, that's our, like our planks, okay? And then you put a piece of wood on it and you try to chop through it. It's pretty hard to chop through if the two planks, the carbon and the chlorine, are close together. But you take like a carbon and an iodine and you create all this space, right? If you think about it, it can become flimsy, right? Because they're so far apart, easier to chop through it. Same concept. So while they are all single bonds, the bond association energy for carbon chlorine is much higher because the two atoms can get closer together because chlorine is a smaller atom than, let's say, bromine or iodine. Questions? Oops. All right. So this is a ball and stick model of two organic molecules. This is C2H2. That's a triple bond. This is C2H4, which I just
Wrong screen.
Oh, sorry. Thank you. C2H4, which is a double bond. So this one should be fairly conceptual, though.
There's gotta be one closer.
Which one has the lowest bond energy? So what does low bond dissociation energy mean? Easiest to break. So that's going to be this guy, right? This is just comparing double and triple bonds. Questions? Easier to break, harder to break. Triple bonds closer together.
I'm just really trying to level up these new guns. I'm good right now.
Why can it get closer? Are you talking about the carbon chlorine? Because chlorine is a smaller atom. So the bigger atoms are, the harder they are to get closer to each other. So carbon, so all of them have carbon in them. So it's not carbon we're focusing on, but chlorine is smaller, which means the carbon and the chlorine can approach each other easier. The carbon and the iodine is huge, meaning it can't get as close to chlorine. It has so many more rings of electrons, right? So let me see if I could draw like this, just to try to visualize it. Wow, wait. So there's chlorine, right? Chlorine's oh wait, is chlorine period 2? Why is my period 2, right? Or is it period 1? Or period 3? Which one's chlorine? Period 2? Okay, 3. Good. I didn't marry. Okay, so then I'll just do bromine instead. And then you got a little carbon right here, right? So like this guy can approach this guy easier than like this guy. Look, it's like big and bulky. It can't get as close to it. So this will be a shorter distance as opposed to this being a longer distance of attraction.
Yeah, we can try that.
R period, no, period 3. Okay. So these are just space filling models. This is obviously a diatomic, right? 2 of the same element, and this is not a diatomic, 2 different elements. Which bond has the lowest bond energy? Well, it's very apparent that this is 2 of the same elements, and this is the same element over here, but with an atom that's bigger. Okay. So if this is a bigger atom, these should be further apart. The 2 nuclei should be further apart, meaning the electrons, because of that, are going to be easier to break apart. Lower bond energy. These are closer together. They will experience a greater force of attraction, or remember, greater Coulombic force. Remember that fancy word, and will be harder to break. All right. So complete the analogy. Bond energy is bond dissociation energy, or bond energy is for covalent bonds. Do you guys remember what it is for ionic bonds, what it's called? What holds ionic compounds together? It's positive and negative. Do you remember what its energy is that holds it together, what it's called?
Yeah, I think I downed them on precision.
Lattice energy, because they form a crystal lattice. So, which of the following bond pairs has higher bond energy or bond dissociation energy? Cl2 or I2? So this one's higher. So what does that mean? Harder to break.
I got some stuff down.
Cl2 or I2? Cl2, smaller. What about N2 or O2? Well, nitrogen and oxygen are actually pretty similar in size. They're right next to each other on the periodic table. This isn't going to be anything that has to do with the same bond, because nitrogen has a triple bond and oxygen has a double bond. So who has higher bond dissociation energy? Nitrogen.
Let's jump down to skull.
Okay.
My bad.
All right. Ooh, remember this? I'm ending with this. So, because we can draw Lewis structures, the bonds broken minus bonds formed is now your job to be able to do with drawing. So, again, remember, breaking bonds is endothermic, forming bonds is exothermic. Okay? So delta H. Breaking bonds. This is endothermic. Minus bonds broken minus bonds formed, which is reactants, bonds broken, and products. So whether the overall process is exo or endothermic depends on these 2 guys. If this is a big number, compared to this number. So if it takes more energy to break bonds than it does that you get out of forming new bonds, the overall process, this guy, is endothermic. However, if it doesn't take a lot of energy to break bonds and you get a ton of energy out from the formation of new bonds, the overall process would be exothermic. So again, breaking bonds is endothermic. Forming bonds is exothermic. Whether the overall process is exo or endothermic depends on these guys' numbers. Oh no. All right, are you ready? So this is how we shall end. I'm sorry I have to end right before break with thermo, but here we are. Ethane is C2H6. We're combusting it, so that's O2, CO2, water. We're going to use bond enthalpies, but see, you can't do this yet until you draw all these structures. So go draw them, and then I will put the enthalpies up, and then you will make sure you get this answer, please. What I'm trying to do is color coordinate all the different bonds we have to take care of, and very, very commonly in combustion reactions with the organic molecule, so many people miss the carbon-carbon bond. Do not forget about the carbon-carbon bond. So look at 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So you have to look up the carbon-hydrogen bonds. So again, it's on my slideshow. Oops. Okay, 413, right? So that's what I'll put in there, 413. So 413. There are 6 carbon-hydrogen bonds, but there's 2 of these molecules. So there's really 12 of them, right? So I put that 2 right here, plus carbon-carbon bond. So you go back. Carbon-carbon is 348. So plus 348 times 2. There's 2 of those. So these are bonds broken, plus 7 oxygen-oxygen double bonds. And again, I'm not going to finish this in time. So oxygen-oxygen double bond. Uh-oh, I don't see it. It's probably cut off. Am I missing it? Oh, O2, 495, right here. It's right here. So plus 495 times 7 of them. So this is my bonds broken minus, and then you do down here, the bonds formed. So the answer is on the slide. Make sure you can get it, and then if you have any questions, you can reach out to me.